Okay, well, maybe it's time to start. So, technical problems are conquered. Three. So, Anton.
No, he's late. He's going to be late.
Hello everybody, my name is Antoine Seguin. I'm a PhD student actually, and I'm working in Laboratoire Fast in France. My supervisors are Yann Berthaud and Philippe Gondret, and we're working on impact in a granular medium. So on this picture you can see a spherical projectile which impact granular media. It can be compared to a meteorite to impact a planet for destruction or things like that. So what I'm going to talk about in this presentation, we are going to consider two sides of the impact. Firstly, we're going to consider the penetration depth of the projectile, and then in the second part we will try to give you some elements of the dynamic of penetration by impact by having a look to the granular medium. So first of all, a little study of the penetration depth. So I will present you my experimental setup, which is a three-dimensional setup, and we're going to look at the confinement, the non-confined case, then the lateral confined case, and finally the normal confinement. So all the results I will present to you have been published, and that's all. So this is my experimental setup. So I've got a projectile here. I drop it from a free fall IH, and then it impacts a granular medium, which is in a cylinder of diameter capital D and depth B. And I measure the penetration depth delta. And I'm going to use another length, which is capital H, which is the total drop 8. It's free fall 8H plus penetration depth delta. And moreover, I'm gonna normalize all the quantities by the diameter of the projectile. So I'm going to talk about normalized delta, which is delta over D, and normalized H, which is H over D. So now we're gonna plot. We're gonna interest to the unbounded case, and we are gonna plot the normalized penetration depth as a function of the normalized 8. And we see that when we change the diameter of the projectile, we have a linear curve in a log plot. That means we can say that the normalized penetration depth is proportional to the normalized 8 to the power alpha, when alpha, and we measure that alpha is about 0.4 in the unbounded case. So now, moreover, we are going to change the density of the projectile, always in an unbounded case. The unbounded case means the diameter of the cylinder can be considered as infinite. So, and we see that if we plot the normalized penetration depth as a function of the density ratio of the projectile, and where here is the density of the granular medium, we also have a linear curve in log-log plot. So that means the normalized penetration depth follow a power law fit, which can be written as a prefactor A times density ratio power to the power beta times normalized A to the power alpha, with this kind of value for the quantity. So this result as applies in unbounded case. And now we're going to confine the experiment. And we are going to see that this confinement has an influence on the prefactor A and the exponent alpha. So that's what we're doing. So here, we decided to change the diameter of the cylinder capital D. And we see that when D decreases, the normalized penetration decreases too. Okay. Before, this was the unbounded case. And we see that when D decreases, the exponent alpha decreases too. Moreover, we also see that the prefactor A decreases too. So the question is, how does it decrease? So let's have a look. First of all, we're going to with exponent alpha. We see that when alpha, we use a quantity capital D over D. So it's also a ratio of diameter. And we see that, as I say, when D decreases, the exponent alpha decreases too. And it's following an exponential behavior of that form. And we note that we've got the quantity alpha here, which is the unbounded case value, which is not surprising actually. And we've got an aspect ratio here, lambda, and this characteristic length characterize the range of the wall effects. Okay. And we can say that when we've got a ratio on about 4 or 5 for this quantity, we can say we are in an unbounded case, which is very important for the next experiment. We can say that over this value, we are in unbounded case. We've got the same result for the prefactor A. Here, we can see that the prefactor decrease when the quantity here with the ratio of diameter decrease too. And it follows also an exponential behavior. And there is got another aspect ratio, which is about 0.7. It's about the same as for the exponent alpha. And we see that for over about here 5 diameters, 5 ratio, 5 for when D over D is about 5, we are also in the infinite case. So that's what we can see. That's what we can see about the lateral confinement. We are able to see the range of wall effects and see their influence on the penetration. So now let's have a look to the normal confinement. So here we are in an unbounded case for the diameter D. That means D is considered as infinite, and we change the value of B. That means the bottom of the cylinder here is changing. So here, when B is very large, here it's the infinite case. The plot here is the unbounded case. And then we decided to change the value of B here, and we see that also the penetration depth follow the previous curve, until it reach the bottom of the cylinder here, and then for each value of b. And here, after the point here, are a rebound of the projectile on the bottom. So here we touch the bottom, and then it's a rebound of the projectile on the bottom. So we doesn't consider this part. So when you see that curve, that means the normal confinement has no influence on the penetration depth. So that means all the forces of the granular media applied by the granular media to the projectile are only radial. So that's what I'm going to say. That's what I'm about the confinement in 3 dimension. And now I'm going to try to give you some elements of dynamics of penetration by impact by, I must say, not dynamics, but rather kinematics. So by using another experimental setup, which is a 2-dimensional one, and then we're going to try to get the velocity field in the granular medium. So here, in my experimental setup, is a LHO cell, which is made with 2 glass here, with a gap B about 5. I can change this gap. Then in this cell, I put a granular medium made of glass beads of about 1 millimeters or 2. I can change. And then my projectile here is a steel cylinder of diameter D. And I drop this cylinder from the height I want. And I make a movie of the penetration of the projectile in the granular medium by using a high-speed camera.
Sorry, can the gap be smaller than the size of the steel cylinder?
What?
It's a dish. Diameter.
It's a
Ah,
disk.
no.
Sometimes it's a disk, sometimes it's a cylinder.
Thank you. Thank you.
So, and this is the kind of movie we have. Here we've got our projectile, we impact the granular medium, and we've got, I am able to measure the depth, the position of the projectile during time. By derivating the position, I've got the velocity, and by deriving the velocity, I've got the acceleration. The problem is the acceleration is very noisy. And here on the velocity, we recognize here free fall, and it's free fall actually, so that's good. And then here's a decrease of the velocity in the granular medium during time. So it's easy to have information on the projectile here, of the dynamic of the projectile here. So now this is more tricky to get information on the granular medium. So we are going to use PIV method to get the velocity of the granular medium. So here, this is how I treat my movie. So we've got an impact. We're going to get the velocity field by using a PIV on the grain here. So now I've got all the velocity on space here. So the question is how to extract some information of that. So this is a very tricky problem because there are a lot of information and you have to treat it very carefully. So first of all, we are going to choose the projectile as a system of reference in polar coordinates. That means here, this is a projectile. If we put at a distance r and angle theta, we are in polar coordinates. So the velocity field here and thus the projectile can be written as that form: a component on ER and a component on E theta. So now here we're going to plot the velocity profile on a line as a function of theta along a line r equal r. We've got a curve. Then we're going to divide. This line is plotted as a time t. We're going to divide by we're going to normalize this plot by the velocity of the projectile at that time t. Here, v over velocity of the projectile. Then we're doing that for all time t, and we see that all the curves can be, all the movie, all time can be put on that curve. And that curve seems to be a sinus. So I decided to model it by a sinus. Okay, and that means, and here it's autoradial component. That means autoradial component can be written as this form, which means velocity of the projectile times sinus theta times an amplitude function of r. We've got the same result for radial component, but I must admit, I must confess, this result are only reliable when the value of theta is between 50 degrees. Over this value, we are sometimes on the ejectas, and this model doesn't work well. So under the projectile, that means in the dense phase, we can use that. So now we're able to plot the amplitude function of r, and that's what we've got. For the radial amplitude, we've got that form here, and here we've got many experiments. We've got 2 experiments, so the results are similar. And we've got that form for the autoradial amplitude. So we decided to model the result here by an exponential behavior, because when you use a simple model of elastic collision, you can find an exponential behavior. And here, by using an argument of conservation of mass, you can deduce that this amplitude can be written with that form. So here, with this model, 3 characteristic lengths appear: lambda, lambda 1, and lambda 2. The problem is I don't really know of what are the parameters that makes these characteristic length evolve. Actually, I changed many parameters like the diameter of the projectile, the gap, or the diameter of the grain. The lambda change, but I don't know how. I try. I'm working on it. So I can say what are the scaling of this characteristic length. So now I'm going to conclude. So in this talk, we see that in 3D experiments, in the unbounded case, the penetration depth can be expressed like this. And the lateral confinement has an effect on the penetration depth of that form, an exponential behavior. And the normal confinement does not affect the penetration depth. Then, on 2D experiments, it is possible to get and model the velocity field of the grain under the projectile during the penetration with that form. So now, what we plan to do in 3D experiment is to get the dynamic of penetration in 3 dimensions, and then in 2D experiments, in order to get the variation of the characteristic length with parameters, we're going to use a numerical simulation. So this simulation I'm using a code made by Jérôme Crassou, and it's possible by using this code to get. I hope to get the information I need. So here you've got a projectile who impacts granular media, and it's evolved. So thank you for your attention.
Okay, yeah. What are alpha and beta in 2 dimensions?
Sorry?
What are alpha and beta in 2 dimensions?
In 2 dimensions, alpha is about 0.3 and 0.28, and for beta, I didn't have a look actually, because it's when in my 2D experiments I use a magnet to maintain the steel cylinder, and I have to if I took another projectile in another material, it's more tricky to maintain it and drop it. So that's why I haven't had a look, but I hope I'm going to do it.
The one at the back.
It was not clear to me from your movie if in the 2D experiments, if below the projectile there is air, or if there is contact with the bits. I mean, it seems there is a layer.
It's but actually on the movie it's very hard to see if there is if the capacity of the granular channel or not. So that's why I'm going to use numerical simulation to get this information more precisely, because on the movie it's hard to get actually.
Could you try to take off the air from your experiment? I mean, to make experiment in vacuum.
Space.
No, vacuum.
I haven't got any money. Give me some money, I'm good. Give me some money.
That has to do with my question. If your height is from which you release the particle is small, I expect that your behavior is slightly different. It may have to do with
you mean when, for example, the value of the free fall is near to
well,
zero?
I think the impact velocity is actually the parameter and not the height. And in that way, you can eliminate the friction due to the air. What was just said? Well,
that's what I said.
well, you get a state. If it's high enough, you get a steady velocity.
Of course.
And then it's not dependent on air on height anymore. So the impact velocity, I believe, is the right variable.
Yeah.
Okay.
Did you have any problems with repeatability? I mean, how were you packing in the sand?
No, because I didn't have a look to compaction. I mean, when I'm doing it, I'm only made the same preparation. I'm stirring on the same way, so my complexity is about always the same, about 0.6.
So you're just stirring it.
Yeah, and just playing it, and that's all. It's hard to. For me, it's not my my priority, and it's hard to control for me actually. So I made other things.
Did you find a way of aerating your granular material before the impact? I mean, I want to see how you could cross over to the LOSA, to the Dutch experiment, where they deposit little h was equal to 0, and they deposited heavy ball on granular material which was previously aerated. And then they had a very interesting experiment with a crater as well, a bubble and a crater which formed, and some jet of bubble as well. But I was wondering, it seems that your dynamics is quite different, but there should be a nice crossover if you decrease h and presumably aerate a little bit your material, prepare your granular material in order to make it less dense. I don't know. It would be rather nice to make the connection.
Maybe, but actually, it's hard for me to change my experimental setup by making aeration of a very fluid hydrogen. And so if I want to do that, I have to change a lot of things. So
You have only half a year before the end of your PhD.
no, half a year. No.
Okay, last one.
So a different question to ask is, and I thought maybe that's where we were going. Do you actually prepare your bed in the same way every time?
Yeah.
So it's and so you really want to have the same density each time. And so you do.
Yeah.
Okay.
And that's what we can see.
It's complicated, it's the condition.
Yeah.
Wow. Just want to say that here, no, not here. Wait, please.
Yes. Nearly.
I said you had some room.
On that picture, what is the diameter of the steel cylinder?
Sorry?
What is the diameter of the steel cylinder?
Here
Is it
it's about 16 millimeters here.
it's not that pale, not that grey dot.
No, the gray dot here is just for me to get the position of the projectile inside. No, that's what I just want to say here. Okay, never mind. Okay, no, I just want to say about preparation here. Here you've got many points, and this curve, the black points, are 3 different experiments with the same velocity. So the results seems to be the same, independent of my preparation. Just to